because I don't want things to be due during break. I've adjusted the due date slightly. Both are going to be due when Monday we get back at 11:59 p.m. That way, in case you decide, I don't think it's the best strategy, but it's a choice. I don't want to do anything from now till after break. You can, rather than making it then. You'll also open at the same time, so if you want to get it done before you even start Thanksgiving break, that's up to you. So that way it's flexible. And in case you plan to do it during break and forget, you still have Monday where I can remind you in class, don't forget to do these two things. So I've set the due dates for your last one, which you quiz to be 11:59 p.m. on Monday we get back. Okay. Also, because I know you'll be studying, while we'll do some review, we'll do just review when we get back. We're going to get through the last topic either today or maybe the very beginning of Wednesday. I wanted to go ahead and give sort of an overview of the exam topics because that would help so you can get ready for your review. So first we have the biggest section will be this. So this will be our stoichiometry and composition of substances section. So that'll be each of these topics. So remember, you got to know the balance chemical equation. Okay, this is chapters 6 and 7. If you want to calculate products from reactants, so that's things like theoretical yield to percent yield. You can have limiting reactant problems. We can use the concept of molarity, so how to go from moles to liters. The definitions of solutions to have some ideas of the concept. You use reactions involved in molarity. You should use solubility rules. I will be giving you a copy of these. You should do acid-base titration. You should have memorized what strong acid bases there are. And then finally, doing things with oxidation numbers, like identifying what's reduced, what's oxidized, and that type of stuff. So this will be a large portion of your exam, probably about 35–40%. Then we have the topics we've been doing more recently. We've got gases. So gas problems where you change one property, both with and without numbers. So for example, you have the relationship P1V1 equals P2V2. You should either be able to answer it if I tell you something like, here's the starting pressure and volume. If you create a new pressure, what's the new volume? Or I should be able to ask it conceptually. So you need to know what's going to be increase the same direction, what's going to increase in opposite directions. So I should be able to say something like, I have a balloon at a particular pressure. I squeeze on it to increase the pressure, what happens to the volume? So something like that, you should be able to answer even without putting numbers in there. You should then be able to do ideal gas problems. So I give you some values, you calculate one of them. We then have stoichiometry with gases. So that's where you do things like limiting reactant problems and theoretical yield or percent yield. But I give you pressure. So you have to use PD equals nRT to find your moles. This also includes you need to do partial pressure problems and mole fraction questions. That will cover everything in the gases section. Then our thermodynamics section, you should do energy calculations. So things like, this is how much work was done on a system. This is how much heat it gave off. What's the energy change? You do Q equals MC delta T problems, where I give you a specific substance, and I tell you something like it's this mass, this is the specific heat of it, here's the temperature change, what's Q? You should do calorimetry problems, that's where two objects are transferring heat, or you have, it may be a chemical reaction transferring that energy. So you should do calculations with that. You should do conversion problems of energy, so that's all our stoichiometry stuff. That's what we did in the last class. And then the last topic we haven't covered yet, but will be today and a little bit of Wednesday, is something called Hess's Law. There are 3 different ways of calculating how much enthalpy change should happen for a reaction, and you should use all 3 of them, and we're going to look at how to do that. Also realize what I didn't put up here, which I'll write some more stuff up here. We have a very small section where you go back and we do hybridization, because we didn't do that on the first exam, if I'm remembering right. We did that right after. So that's the part where you have to be able to identify a molecule as sp, sp2, sp3, sp3d, or sp3d2. You should be able to identify sigma and pi bonds in a molecule. And really, those are the only 2 new things we did there. Note that you do have to be able to correctly identify, create Lewis structures of molecules to be able to do this. So you have to make sure you know your Lewis structure rules, but that's something we already have tested. I won't be explicitly testing you on Lewis structures, but to be able to do them, you'll be able to get these answers. So every question I can think of would presumes into these topics here. So if you can do all of these things, you're in a good spot for that. Okay. So that's all the announcement stuff I wanted to do. So what I'm going to do in terms of timing to make sure, I want to make sure we get a good chunk into the next topic. So I'm going to start with our new topics. If I have some extra time at the end, I might do some review, but we're going to just stick to doing a review on Wednesday and then the weekend. So we're going to talk a little bit more about enthalpy. So to do this, we need some definitions. So first, to define what a standard state is, which we've talked about before, but I just want to remind you to use the term a bunch coming up. So a standard state in general is some common set of conditions that we as scientists have agreed on when we talk about values in like tables and stuff. So for us, a standard state, we've mentioned this before, is going to be pressures of 1 atmosphere, with a little side note, sometimes 1 bar, and I'll just mention what a bar is. 1 bar, you don't have to know this, so let me explain what I'm writing. For the purpose of this class, the answer is pressures are 1 atmosphere. That's everything I'm going to give you. I mention this other thing only because more modern things will sometimes use that instead, or some textbooks have adjusted to it, and so I'm going to use 1 atmosphere because that's also what we've been using for PD equals in our TEAC. So all of the things I'm giving you will use pressures of 1 atmosphere as their standard state, but this is not 100% of the time true. The idea was also is the atmospheres, like, that's an average at sea level, but it wasn't something that was, like, we knew what the number was, but it's not like it's always that anyway. So there was arguments about using a slightly different unit that is obviously very, very close to an atmosphere, not quite the same. So practically for most things, we're doing it doesn't change things a lot. We also talked earlier about how this is usually temperature of 0 degrees C, I'll note. And so this is based on what you're reading. So sometimes it's 25 degrees C. So it depends on, you'll see in like a table will tell you what it would be. So if you're just told standard state with no information, you should assume it's 0 degrees Celsius. I just note that sometimes it'll be 25 degrees Celsius instead because that's way more reasonable. And it depends on where information you're getting, what source you're using, which will be listed because different communities of scientists agree on a different set of conditions of what does standard state mean. People that do thermodynamics usually actually agree on 25, but on gas law people agree on 0. So depends on where you're getting it from. Also, one that we haven't talked about here, but will come up in some of the stuff in enthalpy, is solutions are 1 molar. So when we look at things that will be relevant of knowing what we mean when we say a standard state, will be a 1 molar solution. Now, one thing I also want to point out is there's a symbol we're going to use to represent standard state. So, standard state is represented with something that looks like the degree symbol, with a little o step, such as delta H, this. And so this thing means standard state. The reason this all matters is we're going to be talking about how to calculate the enthalpy for reactions. And there are some assumptions that come into that, and one of them is going to be we'll be looking up in tables where everything's listed in standard state. So for example, if you change the temperature, it's possible for delta H to change a little bit. Technically, delta H is a function that is temperature dependent, as are other ones here. There are times where we're going to tell you we'll make approximations. So for example, in this course, we are not going to try to do temperature dependent changes of thermodynamic quantities. So we're going to assume all these things we hand you don't change significantly when we work at different temperatures. So I'll give you a temperature of 40 degrees and we'll just assume, hey, delta H is probably fine. That is true in many instances, not all instances, especially as you get further away from that temperature. So this is just to mention that this is an area where you work if you end up getting into thermodynamics in some way, either through something like engineering or some area of your research, then this stuff can matter. And so we also want to note that this delta, this thing here, means change. And so the reason we state this is because we're usually looking at a change. We're not trying to calculate an absolute enthalpy or energy. We're looking at, hey, if you go from one set of conditions to another, how much does the energy change in that process? I'm not interested in exactly how much energy an octane molecule can contain. I'm interested in how much energy an octane molecule releases when I burn it in my engine. Now, I'm not worried about, oh, CO2 and water still have energy, but I'm not going to try to burn the water in my car to make energy. So, until I'm trying to do that, I don't worry about its delta H. Just worry about the change to it. The nice thing about delta H standard state values is they can be looked up in tables. And we can also make adjustments. If we have a system that's not at delta H standard state, we can sometimes make adjustments to get it. So that's the reason we're interested in this. So there's a specific type of enthalpy that we tend to look up. And so I want to mention what it is. We're going to add more subscripts because that's how we do things. So we have something called a standard enthalpy of formation. this one at least, I think, makes a lot of sense from the name. That symbol, and then we have a little F. What this means is, what is the energy change to make a molecule? And specifically, to make it, so we'll do that. So this is energy change to make a molecule, or sorry, to make exactly 1 mole of a molecule from substances that are single elements in their natural state. At standard state. In their natural state at standard state. So what we mean, and obviously these are two different meanings of the word state. So for example, if you had oxygen to help you make water, and you want to know the enthalpy of formation, we're talking about gaseous oxygen, we're not talking about liquid oxygen. So that's all that means, and so you break it apart from it. So to give an example of what an enthalpy of formation statement looks like, and there's a reason we're covering this, not just as a definition, we're going to do some stuff with these. So for example, delta H of formation for carbon dioxide gas is negative 393.5 kilojoules per mole. So let's talk about, so what reaction does that statement represent? That's what we're worried about. So the reaction you would get is your product will for enthalpy of formation, the product side will always be just this molecule and exactly 1 mole of it. Even if it causes you to have somewhat strange fractions on the left side, that's because that's the definition of this term, and that's why sometimes, not this one, but sometimes you'll see fractions in your coefficients, when we normally would say that's not a balanced reaction. So this is made of carbon and oxygen. And so, we would say, this is carbon solid plus oxygen gas makes CO2 gas. And in this case, it's already balanced. I don't need to put any coefficient in front of it. 1 carbon, 2 oxygens. And so, that is the reaction that the enthalpy change of formation is negative 393.5 kilojoules. And so for this value here is something you can look up in a giant table. If you need them, I'll give you a table on your exam. And so for any reaction, you can get something like this. So, just to look at some other examples, I'm going to take some molecules and how I would come up with this. So, let's take for another example, a molecule that's more complicated. I'm not worried about the number, let's just write the statement for C2H5OH liquid. So what does its enthalpy of formation statement look like? Well, it's made of carbons, hydrogens, and oxygens. And so, we have to combine these together. So we have 2 carbon solids plus 3 hydrogen gases plus 1/2 of an oxygen gas reacts to form C2H5OH liquid. And that's a enthalpy of formation equation for it. I'll make a note here, because this one feels weird, and it's, of elements you're actually going to encounter molecules, it's the only one that looks weird. Technically, you might see this written in a slightly different way. Your textbook would write this as carbon, solid, graphite, as opposed to carbon, solid, diamond. Because they're technically 2 different structures, and the natural occurring state of carbon at standard state would be graphite. I mentioned this, as you get to more complex molecules, or you start working with stuff, there's things where there's some other condition about how the atoms are arranged, and it's not as simple as just it's a solid, because maybe your thing has several versions of solids, or maybe you start working in very strange circumstances. For example, you take water. I think this one's kind of neat. So if you study water, but you study water specifically under the bottom of the ocean where pressures are super high, water has a whole bunch of interesting phases where the rules change. So there are 8 or 9 different forms of water, and so you would have a clarifying remark next to it. This isn't just water, this is water 7 or something like that. But we generally don't do it because most of these under standard conditions, not crazy high pressures or other weird things, just come in one version of the phase. But carbon specifically comes in the form of graphite or diamond. I mention this not because I'm going to directly test you on it, but because that when you see it, you probably don't know what the hell is that. So that's why this thing has this. You can have other clarifying remarks after a phase sometimes if there is some reason to do so. Also, something that some of the textbooks don't do, I don't expect you to memorize exactly what all the standard states are for things. I think it's reasonable to know that carbon is this, it's a solid form. Hydrogen is a gas, oxygen is a gas, they're both diatomic. Nitrogen is a gas that's diatomic. And honestly, if you have all those, that's really the ones that go up. So, I think that is good enough. Note that I'll show an example, because some of them are ones that is not reasonable, I would not expect you to know for sure. For example, your textbook gives an example of how do you do this for calcium phosphate. And this is one that honestly, the first way that I forgot the natural state of phosphorus, because the answer to this is 3 calcium solid plus 1/2 of P4 solid plus 4 oxygen gas forms calcium phosphate. Now, the thing to note about this, I don't expect you to memorize that P4 is the natural state of phosphorus. What I would want you to do is, if I gave you a multiple choice and gave you 4 options, I want you to pick out which one had the right number of atoms. And to know both that it's okay that this says P4 and this says 1/2. But I would not have a second option that said P2, because I do not, unless I told you in the problem that P4 was its natural state somehow, right? I don't expect you to memorize that P4 is its natural state. So I promise not to give you a trick question that's about you trying to figure this out. So, okay, we want to know this because we want to understand why I'm going to make changes to this reactions to get other reactions. Also, as a reminder from last class, we mentioned that you can make changes to these equations, right? As long as we change the enthalpy values as well. For example, up here with our carbon dioxide, if for some reason I want to know the answer for 2 carbon dioxide, I could double all 3 of these and double this value as well. This is going to come up because what we're going to do is we are going to add together these equations to make other equations. The idea behind this is I can calculate the enthalpy of any particular reaction from knowing a subset of other reactions, rather than having to do a new experiment for every single reaction. One of the ways, that's the second one we'll look at, is you literally just look up all the enthalpies of formation, and then for the molecules you're making, you add those together, and for the molecules you're breaking, you add the negative of them, since if you're breaking them, that's the opposite of forming. This is also why we talk so much about the concept of state functions. Enthalpy is a state function, so all that matters is you take a set of steps to get from one location to the other, and even if it's not what really happens in the chemical reaction, if your reactants and products end up the same at the end, that's all that matters. Your answers should be the same. And then there's one version we'll talk about when we get to bond energies, why that wouldn't always be true, even though, because there's some theoretical approximations we're going to make. So, what we're going to talk about now, we're going to use those ideas, we're going to talk about something called Hess's law. I do not know, I don't care that you know the name of this. The one statement I'll make is knowing the name of this is helpful if, in addition, I'm going to make some extra practice problems here, but this is one of those things where honestly doing a bunch of practice problems help. If you really want to plug it into Google, knowing the word is nice. If you want to have additional practice problems in addition to whatever I give you. So all this is going to say is any process can be written as the sum of several stepwise processes. For a state function. So this is just a fancy way of saying I can add things together and get there. So I'm going to show an example from your textbook, and then we're going to look at some. I think this is this is a topic. The best thing I can do is solve a bunch of examples for you, because as they get harder, it looks a little weird at first, but they're fun. So the idea behind this is, let's say we're interested in this reaction at the bottom. Carbon solid goes to oxygen gas, goes to carbon dioxide gas. If I don't know the answer to that, I can break it into multiple steps that I might know the answer to. So for example, let's say we instead knew the answers to step 1 and step 2 here. So I can say, instead of thinking of just this change, I look at step 1, if I take carbon solid and mix it with half an oxygen molecule, I get carbon monoxide gas. That is an enthalpy change of a negative 111 kilojoules per mole. Now if I take that carbon monoxide gas and I add another half an oxygen molecule to it, I then get carbon dioxide. That reaction is an enthalpy change of negative 283 kilojoules. If I were to add those two reactions together, you'll notice I get 1 carbon solid, which matches this. 2 half oxygens add together to give me 1 oxygen. There's a carbon monoxide on the product side, and there's a carbon monoxide on the reactant side of step 2. So I can cancel those out. Because step 1 makes the carbon monoxide, step 2 uses it up. So if I add these two reactions together, I get a net reaction, which is carbon solid plus oxygen gas makes CO2 gas. Because I can add those two steps together and get this here, I can add their enthalpies together, and that will give me the enthalpy for the reaction. So the idea behind this is we're going to look at sets of these steps, and we're going to figure out how do I organize them to create some net reaction. And so we're going to look at several examples of this to see how I can organize this if you weren't told, if you're just given the reactions, they're not yet organized in a way where you could just add them together. You notice right now these all add up perfectly, but if the information were provided in a way where they didn't add up perfectly, we need to know how to make changes to get it to add up. So let's look at some examples of that. Okay. So I'm going to start with one. So what I'm going to do is I'm going to use Hess's law. To calculate delta H for this reaction. N2 gas plus 2 oxygen gas reacts to form 2 NO2 gas. Now I'm going to say, let's say I don't know that. But what I do know is I have two other reactions. I know if I take nitrogen gas plus oxygen gas, it makes 2 nitrogen monoxide gas. This reaction has an enthalpy change of positive 180.6 kilojoules. I'm also given a second reaction. If I have 2 nitrogen dioxide gas, it can react to break down into 2 nitrogen monoxide plus an oxygen gas. That has an enthalpy change of plus 112.0 kilojoules per mole. So I have these two reactions, and I want to combine them to get the reaction at the top. The way I do this is I look for molecules that occur in only one of these reactions that also occur up here, and I try to make them match up. For example, oxygen occurs in both of these, so I'm going to try to leave that to the end because I'm not sure how to add those up. But this nitrogen molecule only occurs in reaction 1. What that means is if I want it to match the top reaction, these have to be identical because I can't use this second reaction to change the amount of nitrogen. So what that means is this first reaction, I shouldn't change at all when I go to try to add these together. Because I want nitrogen to be a reactant, and here it's a reactant, and they're in the same number. So this reaction, I don't want to change to be able to get the top one. If I go to my second reaction, though, I have 2 nitrogen dioxide over here. It's a reactant. But over here, it's a product. So if I try to add these together, that won't work out, because that makes nitrogen dioxide a reactant instead of a product. I need to change this bottom reaction to turn nitrogen dioxide into a product instead of a reactant. The two things we said we can do to a reaction, we can change the order it's in, or we can change the numbers in front by multiplying by a coefficient. This already has a 2 in front of it, so I don't need to change the coefficient, but I need to change what side it's on, so I'm going to flip this reaction. In terms of writing things when you're doing these problems, like in the in-person test, if you tell me if you flip it or you multiply by a number, it helps me show your work so I can figure out what you're thinking and helps me give partial credit. If you don't tell me what changes you're making, it's very hard to give partial credit on these problems, which is fine if you just get it right, but if you make a small mistake, it can be hard. So when I change that, that transforms the whole reaction into 2 nitrogen monoxide gas plus an oxygen gas molecule react to form 2 nitrogen dioxide gas. And because I changed the reaction order, I have to change the sign. So instead of absorbing 112 kilojoules of energy, that's going to release 112 kilojoules of energy instead. If I look at this, if I were to combine this top reaction and the bottom reaction, I would get this reaction up here. So 1 nitrogen matches 1 nitrogen there. This oxygen add up to 2 oxygen. This nitrogen monoxide gas is a reactant here, but it's a product here. So it's like we did this reaction, made 2 nitrogen monoxide, and then we used it up in the second reaction. So the 2 nitrogen monoxides would cancel, and then my 2 NO2 would be the product I would expect. One way to do this, especially when the reactions have a lot more changes, is I'll rewrite each reaction below and then cancel out things that show up on opposite sides. So I know this one's simple, but I'm going to go ahead and rewrite this to show how I would do that. So I would say N2 gas plus oxygen gas react to form 2 NO gas, and a delta H of positive 180.6 kilojoules. And then I would check that these things cancel, and then I have those add together, and so I get N2 gas plus 2O2 gas reacts to form 2NO2. My check is when I add everything together, do I get my reaction I was going for? If so, I can just add these numbers together, and that's my enthalpy for this question. So I have 180.6 minus 112. This gives me an enthalpy change of positive 68.6 kilojoules per mole. Now, I'm fine if you don't write the positive sign there and you just leave it, as long as you don't write a negative. I'm just used to it because the sign is so important, we tend to designate it even if it's positive, but I won't count it off if you just write 68.6 kilojoules. Now, this one only had a one-step change and only involved two reactions. So I'm going to do another one that's on this level of difficulty. Then we'll look at one that, what do you do when you go up to three reactions? Or maybe you have to make more changes. And then I'm going to do several of these, and then I'll let you try some. So, let's do another. Wait, still writing it down. It's there. So, we're going to look at a second one. We're going to take 2 NaCl gas. Reaction form 2 nitrogen monoxide plus chlorine gas. This has a delta H of we're not sure. What I'm given is that I have two other reactions I can derive this from. I have 2 NO gas breaks apart into nitrogen gas plus oxygen gas. This has an enthalpy change of negative 180.6 kilojoules. The second reaction I'm given is N2 gas plus oxygen gas plus chlorine gas reacts to form 2 NaCl gas. This has a delta H value of positive 103.4 kilojoules. So now I need to make these two match up with this here. So you want to pick things that occur in only one reaction is the easiest way to do that, and then make sure everything else cancels out. So if I look at this reaction, I can say here 2 NaCl is a reactant, here it's a product, and the numbers already match. So I know I want to flip my bottom reaction. For this top reaction, that also matches with the chlorine, right? I want chlorine to be a product here, and it's a reactant here. For this top one here, now nitrogen monoxide is a reactant, but I want it to be a product. So this one I just have to flip both of them. That's all I've got to do, and then we'll get all three of our things. We can also check afterwards, but it's going to make the oxygens cancel out, the nitrogens cancel out like we would need. So I just have to change both of those. So I get N2 gas plus oxygen gas reacts to make 2 NO gas, which has a delta H of positive 180.6 kilojoules. When I flip the bottom one, I get 2 NaCl gas reacts to form N2 gas plus O2 plus Cl2. That has a delta H change of negative 103.4 kilojoules. Now, if I check that things cancel the way I would expect, I have nitrogen on the reactant side and nitrogen on the product side. Those cancel. I have an oxygen on the reactant and oxygen on the product. Those cancel. I'm left with 2 NaCl as a reactant, which matches what we're looking for. And then we have two products, and we get both of them. We get 2 NO gas plus chlorine gas. And so when I do that, I just have to add my enthalpies together. So I have 180.6 minus 103.4. And I get a change of positive 77.2 kilojoules. That's how much it takes to break down if I break down 2 of these molecules, or 2 moles of this, I get 2 moles of NO, 1 mole of Cl2. That will absorb 77.2 kilojoules of energy to do that. So both of these reactions only involve 2 equations and didn't involve having to change coefficients. So what I'm going to look at now is a system that is more complicated, where we have 3 equations to handle, and we have to change some coefficients. So let's look at it so it's something a little more challenging. Looks like. So, and I will say, depending on your comfort level, this might already seem very easy for some people, and I'm sure there's a lot of practice that's necessary for others. It might be like, you still have no idea what you're doing. The best way to go through these is just to look at several examples and then give you some to try. I'm also working on some additional practice problems with this to add the course in as soon as I can. So, let's find the enthalpy for 2N2 plus 5 oxygen gas makes 2N2 O5 gas. We want to know the enthalpy for the change for this. And so I've got these three reactions. I have a hydrogen plus half an oxygen, and I make a water liquid molecule. So that's going to have an enthalpy change of negative 285.8 kilojoules. I then know if I take N2O5 plus H2O liquid, that can form to nitric acid liquid. That has an enthalpy change of negative 76.6 kilojoules. And then finally we have N2 gas plus 3 oxygen gas plus hydrogen gas is how we form 2 nitric acid liquid. That has an enthalpy change of negative 348.2 kilojoules. So I need to take all three of these and make sure everything cancels out and matches up with the thing at the top. So we can identify that oxygen occurs in 2 places, so I'm not going to worry about it yet. Nitrogen only occurs in 1 place. So I know this bottom reaction, I have to have 2N2, and it has to be a reactant. That's the only way to make it match with this. That's the only place it shows up. So since there's 1 here and 2 there, I know I'm going to have to double this. And I'm not going to be able to flip it. That's the only way to make that bottom one look like the top. Then if I look for my 2N2O5, this is N2O5. It's the only equation it shows up in. So to get them to match, this is going to have to become a product rather than a reactant. It's going to be twice as large. So I'm going to have to double this and flip it. Now for my last part, my oxygen, I know that there have to be 3 oxygen molecules here. Well, I'm going to double it. There's going to be 6 oxygen molecules here. And I don't want 6. I only want 5. So I need to get rid of 1 oxygen molecule. And the only equation I can change is this top one. So to get rid of 1 oxygen molecule, I would need to change this from the reactant to the product side, so it would cancel one of these out. And I would need there to be a whole oxygen molecule. So I would need to double this one and flip it as well. And you didn't have to with water. You could also think of it with, you could also think of it with the water molecule. When I rewrite that, there's going to be 2 waters here on the product side that I expect to go away. So I need to have 2 of these on the reactant side to cancel with that. Or you can think of it as there's 2 hydrogens here, and I need to cancel those out. So doubling this and flipping it would work. So any of those 3 could be done to figure out which changes you have to make. For the purposes of doing these types of problems, you'll always be given a set of reactions that can add up to the one at the top. So you don't have to stress if things just aren't going to work out. If you were trying to do this just from looking at a table, you might have to think more, wait, maybe I need to go look up the different reactions. In fact, the molecules, I need to figure out how to make it go away. But for the purpose of solving these types of problems, both on the final and just sort of how assessments should look at them, they will always work to give you the top one. So you know if you make some things work out, the rest have to. So let's make all 3 of these sets of changes. So now I have 2 water liquid, reacts to form 2 hydrogen gas, plus an oxygen gas. That's going to have a delta H change of, we have to double that, just to make sure I get my math right. And we have to change its sign because we're flipping it. So that is now positive 571.6 kilojoules. The second equation, I've doubled and flipped it as well. And so that's going to be 4 HNO3 liquid, reacts to form 2 N2O5 gas, plus 2 H2O liquid. And that's going to have a delta H change of now positive as well. And that's going to be 153.2 kilojoules. 150, carry 1, carry 1. Yeah. If someone finds out I did my math wrong on that one, they can let me know. But I'm pretty sure. And then I just have to double the third one. So that's 2 N2 gas, plus 6 oxygen gas, plus 2 hydrogen gas, makes 4 HNO3 liquid. This has a delta H value of negative 696.4 kilojoules. Try to make it work. So if I check what cancels out, so we've got water liquid here, there's 2 of both, those cancel. We have 2 hydrogen gas on the product side, 2 on the reactant side, so those cancel. We have 1 oxygen gas on the product side, 6 on the reactant side. That means this one gets used up, and And that provides one of these, but I still need 5 from the original reaction. My 4HNO3 liquid here is a reactant, here's a product. Those cancel out. This doesn't appear anywhere else, so it can't cancel. This doesn't appear anywhere else, so it can't cancel. So if I add them up, I get the reaction I was going for. 2 nitrogen gas plus 5 oxygen gas forms 2 into O5 gas. This provides a delta H value of, we add all these together, 571.6 plus 153.2 minus 696.4. This is positive 28.4 kilojoules. So mostly these are just little puzzles where I've got to put together, how can I take a set of reactions and add up to give them another thing? I will also note, one reason why we make sure to cover this exact method of doing this in 1211, because there will be 2 others we're going to show you, and I think the other 2 are easier to do. But this is helpful when you get towards 1212. We're going to be doing this with some other concepts. There's another topic where we do exactly this. You just change delta H into delta G, and then it's the best way to do it. So that's what I mentioned. It did not get flipped, because I kept it on that side. Yeah. Honestly, that's one reason it's good to show work, because I definitely messed these up a lot, though, where I forget to flip something, or I forget to change it, because I took multiply by 2, but I forget 1. So yes, do make sure to show all that, because it helps a lot. Okay. So yeah, that's how we do some of these. So, what I think would be the best thing to do now is for me to show you one and have you work it now. Look at it for a bit, and at least give it a try for a bit. If you can't figure out how to make all the changes, that's okay, I'll go over it. I think it's just good to get some practice. So, this is, you've got carbon dioxide gas plus methane gas reacts to form CH3COOH. We want to know, using these 3 reactions, what will they get if I add them up to get the reaction? So I'll give you a few minutes to look at this one, and then we will look. Well, I'll make a note, because we haven't had to do these changes. You can multiply by fractions too. So if you've got something that needs to get smaller, it's okay to multiply by like a half or a fourth or whatever it is you make them smaller. They don't just have to get